Additive manufacturing or 3D printing is widely used in many industries because it has several business advantages over conventional manufacturing. For example, the same machine can produce very different products, and complex parts that previously required the assembly of multiple parts can now be produced in one step. But like all growing industries, additive manufacturing has its share of challenges. For example, the lack of fusion defects is known to adversely affect the mechanical properties of components. Because the lack of fusion defects originate from multiple mechanisms, physics-based mechanistic models do not adequately describe the formation of these defects. Here we use the available data from the literature, combine it with a physics-based model, propose an easy-to-use lack of fusion index, and identify the hierarchy of the most important variables that are responsible for this defect. A paper based on this work has just been published in the Nature Partner Journal Computational Materials, and at the end of this video we give the details of this paper and indicate how it can be accessed. This is how the lack of fusion defects look under the microscope. The picture is not pretty. It may appear like a piece of Swiss cheese rather than a serious engineering component. The voids are of different shape and size. The large ones clearly affect the ultimate tensile strength, as you see here. In addition, the fatigue properties are also adversely affected by the lack of fusion voids. The lack of fusion defects may be avoided by trial and error, but this procedure is time-consuming and expensive because of the high costs of the powder and the additive manufacturing machines. Mesoscale mechanistic models have also been used to mitigate this defect, although they are based on an assumed mechanism and cannot consider multiple mechanisms for their formation. Powder scale models shown here have also been used to determine the conditions when these defects occur, but they are computationally very intensive and they have not been adequately tested. So here we use data-driven machine learning and synthesize the available data with the physical understanding so far to provide important insights about the formation of lack of fusion defects.
Here we use a novel approach to reduce the lack of fusion by implementing the augmented machine learning strategy and synergistically combining a mechanistic model and historical experimental data. We analyze 101 independent experimental data for aluminum silicon 10 magnesium, Ti-6-4, stainless steel 316, and Inconel 718. We identify 5 important variables that affect the lack of fusion defects. We use a well-tested model of heat transfer and fluid flow in the PBFL to calculate the 5 mechanistic variables. The model is developed based on the rich knowledge base of welding, casting, and metallurgy. The computed mechanistic variables are analyzed using machine learning to forecast the lack of fusion. Furthermore, the hierarchical importance of these 5 mechanistic variables is determined using 3 feature selection indices such as information gain ratio, and Gini index.
The 5 mechanistic variables are dimensionless hatch spacing, dimensionless pore depth, Marangoni number, dimensionless peak temperature, and Fourier number. They can capture the combined influence of process variables and alloy properties on the lack of fusion defect. Because their hierarchical influence on the lack of fusion is useful to help the engineers to identify the proper process condition to avoid this defect. Their hierarchical importance is estimated by the information gain. The results show that the dimensionless pore depth and dimensionless hatch spacing are the two most important variables among those five. Combine the influence of five mechanistic variables. We derived a lack of fusion index using linear regression based on 101 experiment data to predict the lack of fusion defect. As shown on the left, a threshold value of 0.5 can clearly separate the data into two categories, with defect and without defect. Therefore, when the five mechanistic variables are available, this index can serve as a useful indicator to predict and reduce the formation of lack of fusion before doing any experiment. The calculated values of lack of fusion index under various process conditions for different alloys can be used to generate the process maps. On the maps, the red region is unsafe. It means there is a high chance to form the lack of fusion defect. However, the green region is safe for the defect. The maps indicate the susceptibility to voids at different process conditions for different alloys. Also, the high laser power and low scan speed can result in larger pool and reduce voids formation. Also, these maps can guide engineers to select process variables in the green region to reduce void formation.
From the results we showed in this work, the time-consuming and expensive trial and error method in additive manufacturing can be replaced by the mechanistic modeling and augmented machine learning. The methodology that combine historical experimental data, mechanistic model, and machine learning can reduce cost, improve the quality of the printed metallic parts. Our approach will facilitate the printing of new alloys and be attractive to solve important problems in other manufacturing processes. If you are interested and need more detail about this topic, they are available in this just published Nature Group journal, NPJ Computational Materials. Thanks for your attention.